Hello and welcome to my new video on the Euler gamma function. In the previous video we derived the Euler integral. Okay, I called the first video with 1. Now this is the second video in which we will actually apply this great formula. Okay, and the function that we want to integrate is sinus x over x dx. This function is also called the Sinc function. And if you integrate this from 0 to infinity, you will end up having a value of pi over 2. Now you might ask, isn't there another way to just simply integrate this? Actually, there is no elementary function which is the integral of this body. So stated another way, if you take any elementary function which is just a chain of power functions, root functions, sine, cosine, tangent, cotangent, logarithm and exponentials, you will not be able to solve this integral. Okay, in order to do this you need to use a lot of complex formulas, or the one formula that we found, the Euler integral. And when I'm talking about complex formulas, I'm actually talking about complex analysis, and in special the residue theorem. Okay, I know you can derive this result by residue theorem, but I hope you can read, and this is about the gamma function, and we want to derive it by using the formula that we derived and use it on this. Okay, so just write it down, and I used the sinus equation because we seem to have a problem with the sinus, don't we? We don't have a cosinus, but you could do the same ideas for this, the cosinus. Now for the sinus function, in order to get this sinus x over x, or if you just talk in language of a u variable, we need to get sinus of u over u. Okay, now let's start off on the sinus. Here for the b, we will need to have the value of 1, and for this n we will also need a value of 1. Okay, looking at this, we don't have an exponential here, so this has to be 0. A has to be 0, b has to be equal to 1, and n has to be equal to 1. Now the last question is about the s. Okay, and actually what we need to do with the s is we need to let it run to 0. Okay, we cannot plug in s equals 0 in this case, because s equals 0 will give us a definition problem for the gamma function. Okay, so let's have a look at our boundary conditions. We know that n is equal to 1, b is equal to 1, a is equal to 0, and s shall be 0. In the future we will do a limit actually. Now we need some more information. This p, the magnitude of p, we said that this is just a squared plus b squared, which is simply 1, and we need to find the alpha value here, which you can calculate by using tangent alpha. B over a, b is 1 over a is equal to 0, and I told you in the last video that this belongs to a special angle alpha pi half. Okay, now remember what this integral was equal. It was equal to pi half, so it seems to jump in the game somehow, this pi half. Okay, now we need another thing, because I told you already that gamma of 0 is not defined. We need to express gamma of s in another way, using this cool relationship between the gamma function and the sinus function. And actually we will divide with gamma 1 minus s here and replace this gamma s in here. Okay, so let's have a look what will happen. Now I did a lot of stuff. I plugged in the alpha value of pi half. I plugged in p to be 1 and n equals to 1, so they are not important anymore. And this is actually nothing else but gamma of s written in another way. On the right hand side we have this body, because we eliminated the exponential. We said that n was equal to 1 and b equal to 1, so we got this. Actually this is pretty similar to what we want to derive. We would get that by doing the limit s to 0. Okay, so let's have a look what will happen. But before I do that, I will do a little bit of manipulations here. First of all, this pi is very alone, so let's multiply an s here. But you are not allowed to multiply an s. You have to divide with that s too. Okay, and that's what I'm doing. I'm dividing with it. Now this s is still very, very lonely, and it needs a pi over 2, and because you are not allowed to introduce pi over 2, you have to multiply it with pi over 2. Okay, it was in the denominator, so you need it in the numerator. Now you might ask yourself, why is he doing such crappy things? But look at this. We have pi s over 2. This is pi s over 2, and we have pi s, and here pi s. This was the only reason why I did it. And actually you see something very nice appearing here, pi over 2. Okay, so if you know that this integral has the value of pi over 2, then we can suspect that this will have a value, that this body here, this very strange looking body, will have a value of 1. And in order to evaluate that, we need another piece. Okay, so actually I'm doing here the limit s to 0. I will need another body. What you can actually do right now is you can take the limit of gamma 1 minus s, which will give you the gamma of 1. And if you remember the idea of the gamma function for integer values was just the values of the factorial of n minus 1. Okay, the factorial of 1 minus 1 is actually equal to the 0th factorial, which is defined as 1. Okay, so we will get gamma 1 here, and we get two strange limits, okay, which are actually pretty simple, as limit x to 0 sinus x over x. If you go for x to 0, you will have a 1. You can derive this very, very simply by using L'Hopital's rule. Okay, just differentiate this and this. Or there's an even more elementary way. Maybe I will do a video on that, how to prove that without using L'Hopital's rule. But actually you see that this is going to 1, and even the reciprocal value, if you think of it, will take also the value of 1, because it doesn't matter. You can just take the reciprocal and it will be 1 over 1, again 1. So what we end up is having here 1, here 1, and like I told you, the gamma of 1 is equal to 0 factorial, which is defined as being 1, and we end up having this nice and beautiful formula for the Sinc function, for the integral from 0 to infinity of sinus u over u du is equal to pi over 2. Okay, and that is actually concluding our lecture. We cracked the first very hard integral by using this very, very awesome formula derived by Euler, and in the next video you will try to derive the Fresnel integrals, okay, which are very, very important in physics. And I hope you will stay tuned, will watch my videos, and subscribe. Okay, so that's it. See you guys.